Well, so I'm going to try to get a midterm up to you guys by Wednesday. I think it's going to be good. I'll bring it in, or I'll post it or something. I'll give you till next week, maybe Wednesday or Friday. Okay. All right. So where did we leave off? Well, we were talking about discrete groups, and we're talking about discrete subgroups of this group of isometries in the plane. So let's just recall the statement that we had is that that if G is a finite group, subgroup of M, then it's isomorphic to C. Cyclic group with n elements, or the dihedral group. 2 n elements. The idea was that there's some point that would be fixed by elements. That was main. Okay, so today what we want to do is we want to really sort of delve into classifying discrete subgroups of M, not just these are called crystallographic groups, and they sort of are the subgroups of symmetries of some, some sort of regular pattern that you might draw on the plane. So the fact that you can classify them, I think, is kind of neat, and you can use these classifications to sort of generate some of these figures as well. So the first thing we want to do is prove sort of a generalization of this statement that we had for the real line, which is that if we have a discrete subgroup of a vector space of Rn, then in fact we know kind of what it is, more or less, we can sort of say. So this is a general theorem, more general than what is being said in Artin. Although I think I'm just going to restrict myself. Maybe we'll make comment to the general proof, but let's restrict ourselves to the theorem. Pardon. So this is theorem 6.6. Right. I also did, I don't remember, I think I said this last class, I did kind of scale back, cut out a few sections this week, just so we can cover everything. So we won't cover as much as I had initially hoped, but hopefully we'll get a little more time and take our time a little more to understand this. Anyway, so this is theorem 6.5. It says every discrete subgroup so denote by L of so his notation is say B plus or R2 and that is sort of the awful notation actually. Okay, let's just say I'm just going to say R2. Oh, okay. Plus is the addition, is the operation, agreed with addition. Is either, okay, so it's either 1 equaling 0, it's just a trivial group. 2, it could be the subgroup that is just essentially Z times, I'm just going to call it U, a fan of A here. My notation is going to slightly differ from Artin's. Or it could be ZU plus ZV. And here so here U should not be 0. It's a non-zero vector. And here, even V should be linearly independent. That's so first of all, what do I mean when I say a discrete subgroup of R2? Can someone tell me? It's okay. Yeah, what does it mean, discrete subgroup of R2? So I think we have a definition in R, but what does it mean, discrete subgroup in R2? What is maybe in RN?
Maybe around some neighborhood around the point or some element of the group. There's no other element.
Right. Right. So it'll mean that it's sort of at every point, there is a small ball. Since we're in RN, say, we can talk about balls. But there's some small radius ball, such that the only element in that ball is that particular element you're talking about. This is the idea of discrete. Right. Okay, so we have that notion. And I want to kind of make a comment before we prove this, which is note if L is discrete subgroup Rn, and I'll call it B sub F1. W, the ball, radius epsilon, centered at W, then so this is just notation. So, but now, okay, if B epsilon 0 intersect L, that should be epsilon equals 0, then the epsilon of, say, alpha intersect L equals alpha for all alpha in. Why is it true? So why is this statement true? First of all, what is a ball? So ball, just if you want a formula, but I don't know if you really need it. It's the set of all vectors W such that, I've already got that. It's called W tilde, such that W minus W tilde is less than. Okay, you can have the open ball or the closed ball. Let's just do the open ball. If they're closed, you would take less than or equal to. It's just a ball. So why is it true? Why is this guy true? discrete neighborhood. Sorry, say it again, Kale. I
Oh,
can't.
you have the discrete sub. If it's a discrete subgroup, then the ball, then there's not anything around it. So if we intersect it with the ball, it should only contain that.
Okay. So this, so what I'm trying to say with this, let me try to read it off just so we see what I'm saying. So I've got some. This is my discrete subgroup. Okay. My discrete subgroup, and let's say this is 0. And I'm saying around 0, I've got a ball, and the only thing in that ball is 0, right? Now I'm saying I now take notes and I say, what is the radius of that ball? It's epsilon. And what I'm saying is I can take that same radius and put it around any other point, and no other points in L will be in that ball. Same radius. So this epsilon is the same as that epsilon. That's the kind of point of what I'm saying. It's not that I can choose some epsilon for every alpha. It's that it's just if I find one for 0, then I can use that epsilon for every single other alpha. Why is that true? For this. Suppose it weren't true. Okay. Suppose not. And there exists beta in L intersect this ball of radius epsilon around alpha. Beta is not alpha. So here's the picture. Here's 0. Got a disk, right? Radius epsilon disk. Oops. Epsilon disk. Here's my other point here. Here's alpha. Okay. Ah. Do it. Duplicate. Okay. And now I've got beta. Beta's in here too. Both a no. What's wrong? How do I get a contradiction?
Could look at what like alpha minus beta is.
Very good. I can take this vector, which is alpha minus beta or beta minus alpha, whichever, depending on the direction. That's an element, right? These guys are both in my lattice, so that's an element of my lattice. And so, but now, where is that element? That element is somewhere in here. Okay. And this is the displacement vector, but if we think of it as an actual coordinates, this is actually. In other words, in formulas, if we look at the definition here, maybe we'll do alpha minus beta here, doesn't matter. You know, this is less than epsilon. It's a new ball, which means that alpha minus beta is in ball around 0, or ball around 0. This is not 0, and it's an L. That contradicts what this is saying. Make sense? Kind of. Good enough. Okay. Good enough is good enough for me. A proof is different than Arden's, but it does rely on this fact. So I wasn't even thinking to just talk about it, but now I'm glad I did. It makes sense. Hopefully it makes sense. Okay. All right, so now I want to get to the proof of this theorem. So if we're in case one, we're in case one, and we're done. If it's the trivial group, it's the trivial. Let's assume it's not trivial. And let's choose a vector of minimal length. This is not too necessary, but okay. Now okay, let's call it vector, vector name, say call it U. Is a vector in L. Now, why can we find such a vector? Well, there's a proof of that along the lines of what we did in the real case. But it's not too important. It's not too important. Proof would work with this not being a minimal vector, just let's assume this. So let's give U coordinates. So U is equal to AB. I'm going to define a linear map T from R2 to R, where T of XY is just given by a BY minus AX. Pardon me, AY minus B. Sorry guys. AY minus B. So let me rewind this a little bit. What do I want of my vector U? What I want of my vector U is not necessarily that it's minimal, to be honest. What I want of my vector U is that if I look at the real line that goes through U, I intersect that real line with my discrete subgroup L, that this vector U is a generator for that subgroup, for that intersection. If I take that intersection, I have a discrete subgroup of R, like of a real line. And I know I know what that looks like based on what we did before. So I want that U to be of that type. That's what I'm sort of saying, minimal length, but I'm going to leave that. So here, let's make a claim. So claim is that psi L is a discrete sub R. So this is sort of the meat of the argument, and it's a little bit tricky. And so Arden's proof is like a few pages, and it's got several lemmas. So I'm trying to get around that a little bit with this. But I still need to do some work. So what do I need to say here? Well, it's a subgroup of R. That's not hard. It's the image of a, so psi is a linear transformation, right? You can think of this as, by the way, just if you don't believe that it's a linear transformation, you can see that this is, in fact, this just matrix multiplication. It's a linear transformation, meaning that it's a homomorphism of additive groups, in addition to being, you can scale it with reals. So this is a homomorphism, and the image of a subgroup under a homomorphism is a subgroup. So this is a subgroup of R, and we want to show this is discrete. So what we need to show is we need to show that every element has some epsilon interval around it that will only intersect that particular element. So I'm going to prove this claim by saying the following thing. If it's not, psi of L is not discrete, then there's exists sequence of vectors in L to W1, W2 in L such that two things happen. One, okay, psi of Wi is not 0. B for all I. The limit as I tends to infinity, psi of Wi equal to 0. People believe me? Getting up and leaving, I'm out. No. Useful. So what's going to happen here? If this image of L is a subgroup of R. So we have a subgroup of R and we have a bunch of points on it. So this is now, if this subgroup is not discrete, then there's some point that does not have that for every interval of radius epsilon around that red point, I have an infinite number of other points in my lattice in it, right? For every epsilon. If I had a finite number at some point, I could shrink it down to the smallest bit and get rid of them all. So there's some element in this of these red points where that holds. But if there's some element, I can translate that element to 0. I can just subtract, and since that operation of the group will just take all of the other group elements to other group elements, I can just focus on 0. So I'm saying is that if I just look at 0, for every single radius epsilon interval, I have to have an infinite number of other elements. And this is psi, not phi, sorry, psi of L. So if it's true for psi of L, so if it's true for psi of L, then what I can do is I can, just take those infinite sets of points and find something that's sent to them, right? Some W that's sent to it. So that's this sequence W1, W2. I can find some sequence that's actually approaching 0. And of course, I don't want that sequence to be 0, 0, 0, 0, right? So I want to avoid any of these guys actually equaling 0. They're close to 0, but not equal. So what I'm going to do with this sequence is I'm just going to fix it. I'm going to fix this sequence. This sequence could be a sequence that's just sort of, I can imagine in my two-dimensional case. I mean, what is this picture? This is in R. This is in R. I have a picture in R2. I've got a lattice up here. And what am I doing with my T? My T is a projection of sorts. My T is just projecting down to R, R2 to R. And the image of all these red points are the red points on the line. So I could imagine this sequence here being like a sequence that goes up and out to infinity. So I can imagine, even though I'm seeing a sequence that's approaching zero in the real line under the image, I'm sorry, guys, you should have interrupted me. I changed my notes. This is T, not psi. Sorry, guys. I had psi in my notes and thank you. You must be confident and tell me that I'm just full of beans, as I tell my daughter. Sorry, thank you for your politeness, but no thank you for your lack of credit. All right, sorry. Okay, so all of this map that I was calling psi is T. It's this map here. It's sending R2 to R, and you can think of it as a projection. And so what I'm saying is, if I look at that image, I can have something approaching zero, but then when I look above, it may not approach anything. It may be going, approaching the y-axis, but going out to y equaling negative infinity. So it might be sort of equally spaced up here, even though I'm seeing it bunch up in the image. So what I want to do is I want to fix that. I'm going to say, no, that actually can't happen. So how do I do that? So we look at the following kind of complicated looking thing. So far, it looks really easy. So first, let's take a line. So let's let L be the line, which is just all the multiples of this of my vector U, which I was AB, if you'll recall. This is the line through my vector U. So this is just R. This is all multiples of AB of U. Just if you want. Just a line. Oh gosh. Wrong line. 1 minus B. Let's take this. Okay, so this is actually not the line through U, it's the line that's sort of perpendicular to you. And now I want to look at my distance. I'm going to define a kind of a nasty looking thing. I'm going to say take n sub I to be the distance from W sub I to this line. You guys calculus, you know how to calculate this in calculus 1. We're going to divide by the magnitude of U. Use non-zero vector, I can do that. I'm going to do this. You guys know what that is? You're scientists. Floor function. So you write floor of U, or greatest integer function. This is an integer. So what I'm looking for, so let's say this is my U. I'm going to draw the picture so you can see what's happening. So let's say this is U. What's this line L? This line L is this axis. This is this line L. This line L Sorry, guys, I wrote this proof up fairly hastily. I'm worried now that I'm mistake here. Let me think for a second.
I believe you.
No, I don't want you to believe. I want you to believe the right argument. I was really, I didn't like what Arden did, and now I really don't like what I'm doing. But thank you for your confidence. I do want it to make sense to you guys, but of course, since I'm having trouble making sense, I think I did want AB here actually. I did want AB. I'm sorry. But then I need to actually do something kind of like what Arden does. So, sorry. Okay, so I need something like this. Okay. And then I need to actually, before I define Ni, I need to choose actually just need to choose one thing that's, I need to choose a V. Let me tell you what the V is. Okay. Doug, it's gonna be longer than I wanted it. I wanted it to be short. Okay, so now choose. So let's let this be this line, and let's choose V in L, but such that V is not on this line L. Now, it's possible that there are no such V's. If that's the case, then we're in case 2. If the entire lattice is contained on the line L, script L, then we're in case 2. So this is, here we assume not 1 or 2. Okay. And then with this V, so with this V, now I'll define Ni to be this guy. Okay, so now let me draw the picture correctly. This line L, as you'll see in a moment, this line L is indeed set to 0 under T. Because if you look at U, where does U go when I put it into T? It goes to A times B minus B times A. That goes to 0. Of course, it's a linear transformation, so any scale of U then also goes to 0. So this line L here is going to just be sent directly to 0. Now V is some vector that's not in L. So V is somewhere over here. So now, and now what am I doing? I'm saying, all right, so let's say I look at one of my WIs. Okay, this is really embarrassing, but I was right before. This is the worst. I'm so sorry. I'm just going to fix this. I don't trust myself. All right, or should I? I want U here, and I want L perp here, which is the L. I don't really care about V. All right, so I was right and wrong. All right, so what am I doing here? So this is L perp, besides being very confusing. So I've got some W. Let me forget about V for the moment, and let me give you W. So here's my WI, it's way out here. What do I want to, what is this NI? I'm looking for the distance here, okay? And then I'm going to divide by this length, U, by this length U. And I'm going to take the floor function. And so it's basically the number of U's that I can put in here. That's what I'm looking for. All right, good. Sorry. So now why am I trying to find that number? Because now I can define W tilde I equal WI minus NI of U. This is an element of L because WI is an L, and so is U. This is an element. Right. Furthermore, or maybe note, if I take T of W tilde of I, this is equal to T of WI minus NI because of linearity times T of U, but T of U is 0, so this is equal to T of WI. So my point is, so this sequence W1 tilde, W2 tilde also satisfies this A and B up here. Good. However, since we're subtracting this multiple of U, what we see is that this sequence has to be within this, we could say 2U box. We can take a box around here and say, this sequence has to be in here. Because we sort of pulled it down. We pulled it, yeah, okay, it may be escaping to infinity along this line L, but we're subtracting off a multiple of U to bring it back close to this L perp within an inch, within a U's length of that guy. So this sequence now is bounded. This is a bounded sequence. I'm going to let you work that. Okay. Bounded. Okay, but then there's a problem. So we have that this is, so we have this as a sequence approaching 0 and none of them are equal to 0. So it's an infinite set of distinct elements. Okay, so maybe there are a few of them are repeat, but since it's approaching 0, there have to be an infinite number of distinct ones in there. So now I go back to what I said earlier on. There's a single epsilon that I can put around everything. I have it so that it's disjoint from all the others. So what I'm saying is, but there's an epsilon, real epsilon, greater than 0. That this ball of radius, which in this case is a disk of radius epsilon around W tilde of I, that these are disjoint for distinct WI tilde. Why is that a problem? Well, there's a finite area here inside that rectangle, and all the points are in there. I have an infinite number of distinct disks that don't overlap. So if I add up their areas, I should get infinity. But that's fine, but infinity is bigger than finite. Right? This is a contradiction. There's an argument like this in Arden, but it's a bit cleaner, clearly. And I'm really sorry that got turned around there. Okay. So what's the point? So the point is we've shown that the image of L under T is a discrete subgroup. Okay, and so now, so let's let V be an element of L such that T of V generates but you saw that, I mean, this is equal to like R times some number, right? Oh, sorry, Z times some. That's what we showed. Okay. So we have some element V that's generated. So now the last claim is that in this case, so it could be, again, it could be that this is 0, but that would be the case 2. And so we're not in that case. So now we want to claim that L is then equal to Z times U plus Z times V. So let's prove that. So suppose W is an L. Suppose W is an L. And that's T of W. Well, T of W is in T of L. And I'm saying up here that T of L is Z times R. So we can say T of W is equal to some integer times R. It will then T of W minus K times V is equal to, well, again, by linearity, we get this. T of V is R by definition. Let's assume that. I mean, it could be negative R, but let's say positive. Otherwise, take the negative. This is KR, then minus KR. 0. So in other words, W minus KV is in the kernel T. But the kernel of T is just as a map. Okay, so the kernel of T is R, is a line, but we can restrict it since we're just thinking of these as elements of L. We can restrict this to the lattice L. And if I do that, the kernel of T restricted to L is just Z times U, because U is a minimal length on that line. So that means that W minus KV is equal to, I don't know, JU, or W is equal to KV plus J. Okay. Okay, guys. I really am sorry. It's a little bit of a mess. So this part is just pretty smooth sailing. I think the only, I mean, aside from the misdefinitions here, the only thing to sort of to justify here is this bounded bit, but I think that's not hard given the definition of NI. So given the correct definition of NI. All right, so that proves this claim that if we have a discrete group, one of these 3 things is occurring. And the point is that so this is kind of the key result that allows us to understand these discrete subgroups of M. Because M is like if you think of an isometry, it's sort of 2 things combined, right? It's a translation, or it's like an orthogonal linear transformation. You can always kind of look at it as a composition of one of these 2 things. The orthogonal transformation itself may involve a reflection or not, but you can sort of decompose it into these 2 things. So if we're looking at a discrete subgroup of isometries, we're going to want to understand the translation part, and we're going to want to understand what's called the point group, which is the sort of orthogonal So that's where we're going now. Let me just say a couple of things about that. Now let's assume G is an isometry group, so a discrete subgroup. Of M. Then say L is the translation group. If just L is just the set of translations in G. B TB is in G. This will be a discrete subgroup of R2. So this is the translation group, and we say G bar is the point group. G, where G bar is the image of G under pi. For pi is, you recall pi, there's a homomorphism from M to O2. It's just cushioning out by translations. Translations are a normal subgroup. So the point group. So these two things together give us a lot of information about our possible discrete subgroup G. And what we want to do is we want to say, see how far we can get with that. See how much we can learn about it. So there is a proposition, which I think I have just enough time to assert, and it's not, all of the other proofs are not going to be as bad. I will try not to make any proof as bad as that, but all of them are a lot simpler than what that proof was. And so hopefully it'll be a little more smooth sailing from now. The one proposition which we need is, this is 6.5.11, is the following. So it just says that if, let's let G be a discrete subgroup of M. Isometries. And let A be an element of L. This is the translation group. And G bar, an element of the point group. Then we can use this G bar, which is an orthogonal transformation of the plane, and we can hit the element A that we're actually translating by in our translation subgroup. And this is also an element of L. So saying that the point group will act on the on this lattice L of translations. The proof is silly, but you may not laugh at this point. No. You have this relation. So essentially what we're saying is that if we take inverse, you have to you have to do the right translation with this, but if you do the inverse, then you can see that this is an element. So you have to kind of translate your rotation to rotation, but you'll get. This is an element. So TA is in it and row phi is in it. All right, there's a little more to it than that, but I think that is fair enough. All right, so next time we'll continue. Next time we'll actually draw some pictures and see some nice background. Ah, yeah. I'm gonna